So for this little lecture chunk or example problem, since we're focusing on sample problems, I want to look at number 45 from the text. So in here we have a motorboat can maintain a constant speed of 16 miles per hour relative to the water. The boat makes a trip upstream to the marina in 20 minutes. The return trip takes 15 minutes. What is the speed of the current? So underneath this there are some assumptions, and we're going to kind of make a little drawing to make this work. So let me start with, I'll go up and down. So we'll draw the water. And the water flows, rivers move. The direction is from upstream to downstream. And this comes from the idea if you take water and you tip it, it'll run downhill. So the uphill part is where it's coming from, the downhill part is where it's going, and we call that upstream and downstream. But the water has a motion. It has a velocity, it's moving. So if I put my boat here, and I weren't to give it a motor, or just to let it sit, it would move with the water downstream. So as I try to go upstream, the water's slowing me down. Then I turn around and come downstream, the water is speeding me up. And we can see this in the time the boat takes to go. It takes longer to go the same distance upstream than it does for it to go downstream. Now, we have a couple ways of looking at what's happening. The main way you're usually shown this is the distance something travels is equal to the velocity it's going times the time it takes to get there. And this works with rates. Because velocity is miles per hour, meters per second, it's some distance divided by time. So if I multiply my velocity times the time, times cancel and I get a distance. And so the units work for that, even on very small handwriting. And so what we want to see is what's happening to this boat. Now, we're missing some parameters, but they might help us out. So I will look at the distance it takes from the boat to go from its starting point, start, to the marina, and then from the marina to its end point. And what we should notice is those two distances are the same. And so the boat has to travel the same distance. That's going to let us set some things equal to each other. So we need to think about what is happening with the boat. Well, the boat without the water, and so I'm going to say the velocity or the speed of the boat without the water, or what they say is relative to the water, so without the water flowing, is 16 miles per hour. I'm not going to write it mph. I'm going to write it like this so we can see how the units are a rate, something per something else. Rates pop up. But the water has an unknown, so we'll say x miles per hour. So when the boat's going upstream, that water is slowing it down, and so I'll make upstream, I'll make that a green here. And so upstream, the total speed is VB minus VW. The water is slowing it down, times the time it takes to go upstream. And what did we say the time it takes to go upstream was? It was 20 minutes. Yep. And the time it takes to go downstream, give it a little d here, is 15 minutes. So this equals the first distance. From the start to the marina, we get the boat traveling against the water. The water is slowing it down. It's subtracting from its velocity times the time it takes to get there. If we were to go back downstream, and I'm going to change downstream to some annoying version of blue, because I can. So downstream, now the boat is being boosted by the speed of the water. The water is helping it go faster, and the time downstream. And so we have two things we know, but there's our fact that the distances are the same. And so because these are equal to each other, or the distances are exactly the same, I can turn this into one equation, which is going to help us. So I'm going to pull this here. We're going to go up to our variables at one point and back down to our equation, but we'll make a bigger equation here. So our bigger equation, due to the fact that the distances are the same, is the relative speed of the water slowing it down, the boat down as it goes upstream, times the time upstream, is equal to the water speeding the boat up so we have the boat plus the boat speed plus the water speed. And the time it takes to go downstream. Well, what's nice about keeping track of all these things, if we come up here, we have both times, and we have the speed of the boat. So we'll have both times, this time, and the speed of the boat. The only variable it leaves left unknown is the velocity or the speed of the water. So we can put our numbers in now with, so we get 16 miles per hour minus the velocity of the water, which is what we're trying to find, all times 20 minutes. But we have miles per hour as our speed of the boat. So we need to get our units to work together. So 20 minutes is 1/3 of an hour. Yes, I had to throw fractions in. And 15 minutes is 1/4 of an hour. My pen is dying on me here. I'm going to replace the batteries, but we'll finish this discussion first. And we'll get there. All right, so 1/3 of an hour to go upstream. Maybe I'll replace the batteries. And to go downstream, let's see here. Oops, that's going to be the 16 because the speed of the boat is 16 miles per hour. So I'm filling in my variables here. Just give me a second to get them in. We'll combine our terms. Remember, the thing we want to know is the velocity of the water. How fast is the current going? And downstream, it only took 15 minutes or a quarter of an hour. Okay, here comes a mathematical trick. I want this variable. I can distribute my 1/4 into each of these and deal with fractions, or I can clear the fractions and immediately find a common denominator. And so the common denominator would be 12. So I would need to multiply this side by 4/4. Or multiply it by the 12 completely. So 12 times 1/3 on this side. And 12 times 1/4 on this side. So what I'm doing is taking what the denominator of each term is and multiplying it across both sides. Whatever I do to one side, I do to the other. And so what this gives me is 16 minus the velocity of the water times 4. And 16 plus the velocity of the water times 3. And now I don't have fractions to deal with. Well, I don't have fractions to deal with while I solve the problem. They might come up in the end here. So let me scroll this up to the top. I'm going to distribute my 4 across. And so I have 64 minus 4, the velocity of the water, equals 48 plus 3 times the velocity of the water. I'm going to keep my velocity of the water positive, so I'm going to add 4 to each side, 4v to each side. So I get 7 times the velocity of the water over here. Let me make my v better. 7 times the velocity of the water plus 48 on my right-hand side, and lowly 64 sitting out there. So subtract 48 from each side. And the velocity of the water is 16 divided by 7, or approximately 2.23 miles per hour. And so here we have a unit velocity or speed that is given in a rate. So velocity is miles per hour. That rate, when multiplied by time, gives us distance again. And so here we have the concept of rates coming back up. Some fractional relationship that when we multiply them by something else gives us the top term. And so this is why we discussed unit measurement and what units were, because we're taking reality and we're measuring things in reality and it's changing.